In this lecture, let me introduce one additional synchronization primitive, which being known as semaphores. I already presented a couple of synchronization primitive. One is lock for the mutual exclusion. The other primitive is a condition variables for the synchronization ordering. This semaphores you can consider this semaphore as more unified synchronization primitive that like an umbrella, the lock and condition variable as one unified interface. Let me first explain the API, the interface of the semaphores. You first need to include the header file semaphore.h, and then you can define the variable s. The type of this s is a sem_t, and this variable s should be initialized using the sem_init API. You need to pass the address of this variable s, and the second argument is a 0. That means this s can be shared amongst the computing threads, and this 1 is the actual value to initialize the semaphore counting value for this s. This third argument can be any positive value, integer value, and whatever value being passed as an argument, the value for the counting for this sem type will be initialized to that value. The next two important APIs is a sem_wait and sem_post. When we study condition variables, I introduced a couple of important API, which is the analog of the sem_wait and sem_post. One is pthread conwait, the other one is pthread consignal. Unlike this sem_wait, which only expecting one argument, which is the pointer to the semaphore variable, this pthread conwait expecting two arguments. One is pointer to the condition variable, and also the pointer to the pthread lock. So using the pthread conwait, a little bit complex than the sem_wait. The definition, the semantic of the sem_wait and sem_post are much cleaner than the pthread conwait and pthread consignal. First, sem_wait. There are two actions associated with sem_wait. First, decrement the counting value of this s by 1. After decrement the value s by 1, and wait if the resulted value of the semaphore is negative. Wait means sleep. These two actions is done in one logical atomicity. In case if you do not understand what I meant by the logical atomicity, please listen. Please watch my lecture on lock for the mutual exclusion, and it will detail what I meant by one logical atomicity. The next API is a sem_post, and this has two actions. One is increment the counting value of the semaphore by 1. If there are one or more threads waiting, sleeping on this semaphore variable, then wait 1. It doesn't say which one, just simply wait 1. That is what sem_post does. Likewise, like a sem_wait and this sem_post, these two actions also need to be done as one logical atomicity. Then again, why the semaphores as new synchronization primitive? We already studied the lock and condition variable as a synchronization primitives. Why we need to study something else, such as semaphores? The one outstanding reason is this semaphore unifies these two synchronization primitive, lock and condition variables, into one unified framework. That is the most outstanding reason. Second reason is the semaphores is a counting synchronization primitive. Counting means this semaphore can be associated with any positive integer value. Why this is good? Because in case there are multiple resources which being shared among the several computing threads, then those multitude of the resources can be represented easily using the semaphores counting value. That's the second outstanding reason to use these semaphores as the synchronization primitive. Summary: this semaphores is a generalized, unified synchronization primitive that combines lock and condition variables, and this semaphore interface can be used to represent the sharing, the multitude of resources amongst the computing threads. The following is the list of objectives of learning semaphores in Chapter 31. My main focus of lecture semaphores is how to use these semaphores to solve many outstanding problems in concurrent algorithm via semaphores. Well, to make your feet wet quickly, let me demonstrate how to use semaphore to achieve the mutual exclusion. For this demonstration, I created some sample file under the linprog. Please SSH to the linprog. In my home directory, tilde means UH is my username, user account in linprog. Go to my home directory COP4610, pthread in particular, chapter 31-semaphores-example. Please edit fig 31-5.c. Let me explain what this sample project is about. In the main, I create two threads, T0, T1, and each thread will thus increment this global variable sum by 1. How many times? Whatever number of times which pass as an argument. Since I set this args as 100,000, so after these two threads increment this shared variable sum correctly, then sum should be printed as 200,000. Now obviously we learned about the race condition. So if there's some unwanted interleaving happens in this INCR routine, then the final outcome for the summation may not equal to the 200,000. So let's build this project and let me demonstrate. This may incur some race condition. Therefore, we might have some error messages from this assert line. And let me run fig 31-5. Now, as you can see, the sum is not equal to 200,000. Instead, it's 121,840. Why this happens? Because thread 0, thread 1, these two threads competing to update the sum. Whenever some unwanted interleaving during this update, then the final summation value may not equal to the 200,000, which is being learned while I'm presenting the lecture on lock, mutual exclusion. So let me go back to the project source. And the actual interleaving happens where? Right there. Sum is assigned from sum plus 1. First, you should be able to recognize this sum is a shared variable amongst thread T0, T1. And also, this increment and assign is a two separate motion instruction. First, you need to read the value sum, and then adding 1 to it, and the resulting value being stored back to this shared variable sum. In fact, even though this is one C statement, but in machine instruction, the minimum 3 instructions needed to read followed by update. What I meant by interleaving is, during the execution of these 3 machine instructions, the timer interrupt can come any moment. Whenever the timer interrupt comes in between during the execution of these 3 instructions, then we have race condition. To guard against this race condition, race problem, we need to treat this sum plus 1 assigned to the sum as one critical section, and then we need to add some other, the lock primitive, which is grab the lock and release the lock after this update. In other words, we need to treat this loop body as a critical section. What I would like to demonstrate is, I would like to use the semaphore, how we can create the lock primitive. In other words, how we can achieve the feature of the lock using the semaphore. For your understanding, I'm going to type very slowly. As a first step, we need to include the header file, which is a semaphore. Don't use the plural. You need to use a singular. Otherwise, you will have the syntax error, semaphore.age. Now, we need to define the global variable semaphore. The type is sem t, which is a type of the variable, and I will name that variable as s. After we define this global variable semaphore, we need to initialize this semaphore. So I will do that in initialization in the main. So what's the API? Sem init. And pass the address of the global variable semaphore s. And 0 indicate this semaphore s being shared among threads. So please use the 0 as a second argument. The third argument is the initial value for this s semaphore. We try to achieve the feature of the mutual exclusion, locking, right? So lock is, we only have a two state, lock or unlock. So I'm going to initialize this value as 1. That means initially no one is grabbing this lock. There's only one value for the lock, which is 1. 1 indicates it is a lock, and 0 means, So 1 means nobody having the lock yet. So the 1 means the lock is available. 0 means someone is already occupied the lock. So sem init. The next one is, once we initialize this semaphore as a lock, then since we already identify this sum plus 1 is as a critical section, sem what? We need to wait on s. And after update this sum, sem post, we need to release, right? S. It's wrong. The argument is what? We need to pass the address. So let's say that means initially the log is open because s was what? Initial value is 1. Let's assume that t0 start running. It can enter. It can grab this log s. What is the sem wait? Decrement the value of semaphore s by 1. And then if the value of semaphore is negative, then it sleep on this semaphore. Initially, the value for the s was 1. So sem wait is decrement the value. Now, after it returned from the sem wait, the value for s is 0. It entered the critical section, and it is about to update 1. Let's assume that T1 is having time for the CPU. It tried to grab the lock s, but s is already 0. It decremented the value of semaphore s by 1. So now semaphore is what? Value is minus 1. If the value of semaphore s is negative, it is negative, so it sleep on this semaphore s. Clear? Now, let's get back to, let's assume that T0 gained the CPU. It resume execution from the sum plus 1. So sum is increment by 1. After this one, sem post s. What does this sem post do? Increment the value of semaphore s by 1. So now s is 0. And then if there are one or more thread is waiting, wait 1. And T1 is sleeping on this s. It make the thread 1 being ready. That doesn't mean the CPU is immediately assigned to the thread 1. It simply wake one thread sleeping on this s and make that thread is ready to run. Likewise, the pthread consignal, which is identical. So after waking up one of the thread from this semaphore variable s, whoever run first is the total discretion of the scheduler. Anyway, so this is the two primitive how to grab the lock and release the lock using the semaphore. So let me save this one. And let me make it, and then let's run it. 5.exe. 31-5. Now, sum is correctly updated to the 200,000. So this is the use of semaphore together with the sem-init, sem-wait, and sem-post, and I just demonstrated how to use this semaphore to achieve the functionality of the lock, which is mutual exclusion. So in other words, we don't need pthread lock. By using one API, which is a semaphore, we can achieve the mutual exclusion. This time, let me trace in detail how this sem-wait and sem-post is working. Since this line number is 15, and how this sem-wait, sem-post can resolve the issue of the race, which being happen without the sem-wait and sem-post. So let me move this code a little bit to the side. Let me bring in another slide to the top, and then let's start running. So initially, the semaphore value was initialized as 1. Let me just make the font bigger so you can read better. So 1, initial value for the semaphore. And let's assume that thread 0 is initially running. So state was running. And where is it? Let's assume that the thread 0 is invoked the sem-wait. Okay, call sem-wait. Since the initial value of the semaphore S was 1, so sem-wait return immediately. Why? Because sem-wait, what's the semantic of sem-wait? Decrement value of semaphore by 1. As long as it is not negative, then it return immediately. So it running. I will just, and it enter this critical section, and it try to update sum by 1, right? And let's assume that some unwanted timer interrupt comes in. Okay, so it enter the critical section. Run in, and timer interrupt comes in. This timer interrupt will make this T0 as ready. In the meantime, all those motion state for the T1 up to this point was ready. Ready. And as soon as the timer interrupt to make this T0 is ready, then T1 has turned for the CPU, now running. Alright, when the T1 start running, let's assume that T1 gets to the line 15, line what? This is line 14, sem-wait. It invoke call sem-wait. When it called the sem-wait, what happens? It decrement. The semantic of sem-wait is a decrement semaphore value by 1. As a result of sem-wait, semaphore value will be -1 after the decrement. And inspect the resulting value. If this is negative, then the T1 is sleeping on the semaphore value. So after the call wait, what happens? Since sem-val s is less than 0, so now it is sleeping on the semaphore. So far so good. Since the T1 is sleeping on the semaphore value S, as a result of this one, T0 start running. Where it resume execution, since the timer interrupt comes in during the execution of the code in the critical section, which is increment the sum and update the sum. As a result of this, the T0 is able to complete this critical section. So it resume here. What's a good way to put? So this was ready. This was as soon as it's sleeping. As soon as it's sleeping, that means that T0 is running. Please make sure this is a state. I'm representing the T0. So as soon as the T1 is sleeping, that means the T0 start running. And it just resume from this critical section, and it complete update the sum. It finished the line number 15. The next one is what? Call SemPost. What the SemPost do? It increment semaphore value by 1. Now it's a 0, and it wake up any of the thread waiting on this semaphore S. Since T1 is sleeping on this semaphore S, so it will make this T1 as ready. You need to be able to differentiate between the state running and ready. The T1 is simply sleeping on this S. Now it is woken up by the T0, because T0 just issued call SemPost. So the thread T1 is ready to execute. It needs to stay in the ready queue until the CPU scheduler is actually assigned the CPU to this thread 1. Right after this SemPost from the T0, it needs to go back to the top of the loop, increment I, and then it enter the loop body again, and about to execute same way. Let's assume that there's another timer interrupt comes in. That will make this thread 0 as put into the ready queue. This means T1 start executing. Please make sure, what was the last time the saved program counter for the T1? T1 was sleeping on S. It was inside of this same wait routine. Once it is woken up, then it is returning from the same wait, and then it enters the critical section. You understand? The line number 15 is the returning address for the T1 is inside of this same wait. Since the same SemPost is actually make this T1 returning from the same wait, so it enter the critical section and it update the sum. All right, so it enter the critical section. After it returning from the same wait, the next one is it enter the critical section. And it complete the critical section and SemPost. What does the SemPost do? It increment the semaphore value by 1. So it was 0, 0, 0, up to the SemPost. After the SemPost, the semaphore value will be incremented by 1. If any thread is waiting on this semaphore, wake him up or wake her up, and to put whatever waiting thread, sleeping thread, to the ready queue. But there's no one is sleeping, so semaphore value is 1, and the T1 is immediately returning from the SemPost. So all these is running, and this was ready. Ready? And you can continue, all right? What I would like to highlight is the changes in this semaphore value and what actually happening by the sem_wait and sem_post. And try the different interleaving, whether the solution that I presented actually make the problem resolved. What problem that I'm resolving? The race condition, because this updating this incremental sum by 1 and updating the value sum, these require 3 merging instruction. When the T0, T1 computing for this critical section, then we have the race value, race condition. To guard against that race condition, I use the semaphore as using the 3 API, sem_init followed by sem_wait and sem_post. Before I just give you the chance to perform this exercise, this trace, make sure the most important lesson that you need to learn is what should be the proper value that you pass for the third argument. What's the initial value for this s? For the log, I use the 1 because the 1 represents the log is available. 0 means the log is closed. So when you use this semaphore variable, you really need to understand what should be the initial value for this s.